Ever wondered how your body processes food or how medicines are made? The answer often lies in a fundamental chemical process, organic redox reactions. These aren't just abstract concepts from a textbook. They are the invisible engines driving countless transformations around us, from the simplest biological functions to complex industrial syntheses. In inorganic chemistry, redox is all about electron transfer. But in the organic world, it's often simpler to think about changes in bonding. We look at the number of bonds to hydrogen and oxygen, or other electronegative atoms, around a carbon center. This perspective makes understanding these crucial reactions much more intuitive. Oxidation in organic chemistry typically means increasing the number of bonds to oxygen or other electronegative atoms. Conversely, it can also mean decreasing the number of bonds to hydrogen. Think of it as adding oxygen or removing hydrogen from a carbon atom. This change fundamentally alters the molecule's properties and reactivity. Reduction, on the other hand, is the exact opposite process. It involves decreasing the number of bonds to oxygen or other electronegative atoms. Alternatively, reduction can be seen as increasing the number of bonds to hydrogen. Here, we are essentially adding hydrogen or removing oxygen from a carbon atom. Let's dive deeper into what oxidation looks like for organic molecules. A classic example is the conversion of an alcohol to an aldehyde or ketone, and then further to a carboxylic acid. Each step involves increasing the carbon's bond count to oxygen. This progression demonstrates a clear increase in the oxidation state. Primary alcohols, for instance, can be oxidized to aldehydes. With stronger oxidizing agents, these aldehydes can then be further oxidized to carboxylic acids. This transformation is vital in many industrial processes and biological pathways. It allows for the creation of diverse functional groups. Secondary alcohols oxidize to ketones. Unlike aldehydes, ketones cannot be easily oxidized further without breaking carbon-carbon bonds. This difference in reactivity is a key characteristic used in synthetic chemistry. Understanding these distinctions is crucial for predicting reaction outcomes. Tertiary alcohols are generally resistant to oxidation without breaking carbon-carbon bonds. This is because the carbon bearing the hydroxyl group has no hydrogen atoms directly attached. This stability highlights the importance of hydrogen atoms in typical organic oxidation mechanisms. Now, let's explore the realm of organic reduction. This process often involves adding hydrogen atoms across double or triple bonds, or replacing oxygen atoms with hydrogen. It's about making molecules more saturated or less oxygenated. Reduction is just as critical as oxidation in synthesis. Aldehydes and ketones can be reduced back to primary and secondary alcohols, respectively. This is a common and incredibly useful transformation in organic synthesis. It allows chemists to interconvert functional groups with precision. Many reducing agents are available for this purpose. Carboxylic acids and their derivatives, like esters, can be reduced to primary alcohols. This requires stronger reducing agents due to the higher oxidation state of the carbonyl carbon. This reaction is a powerful tool for accessing alcohol functionalities from more oxidized precursors. Alkenes and alkynes, which contain carbon-carbon double and triple bonds, can be reduced to alkanes. This process, known as hydrogenation, involves adding hydrogen atoms across the multiple bonds. It's a fundamental reaction in the petroleum industry and in food production. To perform these transformations, we need specific chemical tools. Common oxidizing agents include chromium-based reagents like chromic acid or pyridinium chlorochromate, often abbreviated as PCC. These are powerful and versatile for alcohol oxidation. They offer different levels of selectivity. Potassium permanganate, another strong oxidizing agent, can oxidize alcohols, aldehydes, and even alkyl side chains on aromatic rings. Its reactivity makes it useful for a wide range of transformations. However, its strength can sometimes lead to over-oxidation. Peroxy acids, such as metachloroperoxybenzoic acid, MCPBA, are excellent for oxidizing alkenes to epoxides. They are also used for the Baeyer-Villiger oxidation of ketones to esters. These reagents provide a controlled way to introduce oxygen atoms. Other important oxidants include ozone for ozonolysis of alkenes and alkynes, and various metal oxides. Each oxidizing agent has its own specific applications and limitations. Choosing the right one is key to successful synthesis. For reduction, we also have a diverse toolkit. Lithium aluminum hydride, often abbreviated as LAH, is a very strong reducing agent. It can reduce carboxylic acids, esters, aldehydes, and ketones to alcohols. Its power makes it indispensable for many syntheses. Sodium borohydride is a milder reducing agent, typically used for reducing aldehydes and ketones to alcohols. It does not usually reduce carboxylic acids or esters. This selectivity is incredibly useful for reactions where other functional groups need to remain untouched. Hydrogen gas in the presence of a metal catalyst, such as palladium, platinum, or nickel, is used for catalytic hydrogenation. This method effectively reduces alkenes, alkynes, and aromatic rings. It's a clean and efficient way to add hydrogen. Other reducing agents include diisobutyl aluminum hydride, DiBAL-H, for partial reduction of esters to aldehydes, and various dissolving metal reductions. Each reducing agent offers unique advantages in terms of selectivity and reaction conditions. Let's bring this to life. When you consume alcohol, your body uses organic redox reactions to process it. Ethanol, a primary alcohol, is first oxidized to acetaldehyde by the enzyme alcohol dehydrogenase. This is a crucial step in detoxification. Acetaldehyde is then further oxidized to acetic acid by aldehyde dehydrogenase. This acetic acid can then be safely metabolized. This two-step oxidation process is a perfect example of how biological systems utilize redox chemistry. It highlights the body's sophisticated chemical machinery. Consider the grand cycles of life on Earth. Photosynthesis is a massive reduction process. Carbon dioxide, a highly oxidized carbon compound, is reduced to glucose, a more reduced form of carbon, using energy from sunlight. Plants are essentially performing a large-scale reduction. Conversely, cellular respiration is an oxidation process. Glucose is oxidized back to carbon dioxide and water, releasing energy for the organism. This fundamental biological cycle is entirely driven by organic redox reactions. It's a continuous dance of oxidation and reduction. Think about the food in your kitchen. The browning of a cut apple or the rancidity of oils are examples of unwanted oxidation. Oxygen from the air acts as an oxidizing agent, reacting with organic molecules in the food. This leads to undesirable changes in flavor, color, and texture. Antioxidants like vitamin C and E are reducing agents. They prevent or slow down these oxidation processes by reacting with free radicals and oxygen. This is why they are added to many processed foods and are beneficial in our diets. They protect our cells from oxidative damage. In the pharmaceutical industry, organic redox reactions are indispensable. Many drug molecules are synthesized through a series of carefully controlled oxidation and reduction steps. For example, the synthesis of cholesterol-lowering drugs often involves selective reductions. Creating complex molecules with specific biological activities requires precise control over functional group transformations. Redox reactions allow chemists to build intricate molecular structures step by step. They are fundamental tools in medicinal chemistry. Understanding organic redox reactions is not just for chemists. It's about comprehending the world around us. From the energy our bodies derive from food to the synthesis of life-saving medicines, these reactions are everywhere. They are the fundamental language of chemical change. Mastering these concepts provides a powerful framework for predicting reactivity and designing new molecules. It opens doors to innovation in medicine, materials science, and energy. The dynamic dance of oxidation and reduction is truly at the heart of organic chemistry.